and less time consuming for you. Okay, so we will go live in a few seconds. Okay, good morning, good afternoon, good evening, or generally good day. It is my pleasure to introduce to you Rob Hyndman with his talk on, of course, forecasting. And when introducing Rob, I can start with academic achievements, with multiple contributions to the field. But actually, I want to share you my personal story with Rob. So I know Rob from I was actually introduced to Rob from his blog Hindsight when I was just going into the field of the data analysis, and and I and now, right, as academic, I can really appreciate the time and energy Rob is spending on writing his blog and making this resource as free and as available as possible. So if you don't know this page, please check it. Hindsight is a great source of knowledge about forecasting, but also other topics like, for example, LaTeX. And I think this is a really a great resource to dip in. So without further ado, we are very happy to have Rob on the board at this edition of YR. Great expert in forecasting, and I am really looking forward to his talk. Rob, the floor is yours.
Thank you, Mikhail, and it's a pleasure to be here. Would have been nice to be in Poland again, but that's not to be at the moment. So maybe in a future year I can actually come back to Poland, as I was there in 2016. So let me begin by sharing my screen. And okay, so hopefully everyone can see that okay. And I'm going to talk about some packages that I have been working on in recent years that are, I think, an improvement and an extension on some of the stuff that I've done before. So those people here who do forecasting and who use R have probably come across my forecast package, which is the most widely used software in the world, I think, for forecasting. So I'm no longer developing that because I wanted to start again and do something a little different with a lot of the same functionality, but a little easier. And I'm going to talk about those packages today. So to begin with, let me just talk a little bit about why we wanted to do this. It was partly around the changing nature of time series data. Before I talk about that, though, let me just mention the package names. So rather than have one package, we've actually got three main packages that work together, and they work with the Tidyverts collection of packages that RStudio is famous for. So the three packages are Tibble, Feasts, and Fable, and I'll talk briefly about each of those today. Tibble data is sort of an extension package that provides data sets in the same format. If you go to the tidyverts.org website, a link at the top there, that's where you'll find information about all of the packages. Tidyverts stands for a tidy version of time series, and there's obviously a play on the name Tidyverse, which RStudio uses for their collection of packages. Okay, so here is a data set. This is half-hourly electricity demand data from Victoria, the state I live in Australia. And you can see there's a timestamp here, which is a half-hourly timestamp. The state, Victoria, there's actually, this is for the whole of Australia, so there's 8 states and territories. So the top of the data set is Victoria. That's the date, whether it was a holiday or not, and the 1st of January is always a holiday in Australia. The temperature on that day, the maximum temperature in Melbourne, and the total demand for electricity in that half-hour period for that location. So you can see that, you know, it's not like the sort of time series data that most universities teach, which tends to be annual, monthly, or quarterly, and relatively simple, one series and not too long. This collection of data has a few features. There's a time index, which in this case is half-hourly. There's more than one series here. There's actually 8 series, but sometimes we have millions of series in one data set with different key to identify them. And we have a bunch of other bits of information, which are the time series measures, which are usually the things, or some of them are the things we want to model. In this case, we might want to model demand as a function of temperature, for example. So notice that it has has a time index, it has a key, and it has some measures. And we call this a tibble, which stands for a time series tibble. And you can see at the top of the screen that it tells you that there's 420,000 rows, there's 6 columns, there's 30-minute data, it's just what's in square brackets, and it gives you the time zone that the data is collected in. So this timestamp relates to this time zone. So my previous package, you couldn't model a data set like this very easily at all. It's not set up to do this. Let me show you a different data set. This one is, again, an Australian data set. Most of my data is Australian because that's where I live and I tend to work with Australian organisations. So this is data on Australian tourism regions. So that's a map of Australia. I live here, right down the bottom in Melbourne. That's one of the 2 largest cities in Australia. The coloured regions are the 8 states and territories, and the other, you can see that each state and territory is divided up into smaller regions, which are regions that we use for studying tourism. Okay, that this particular data set is quarterly data, so it's not particularly high frequency, unlike the previous one, but there's a lot of series here. The data is split up by the states and territories and by regions and by the purpose of travel. So when you take into account all of the different ways you can split this data set up, there's actually a lot of series that are being modelled simultaneously. In fact, there's 304 series. So you can see that there's an index, which in this case is a quarterly index. There's 3 keys here, which is region, state, and purpose. And there's 304 unique combinations of region, state, and purpose. So there's 304 individual series. And in this data set, there's just one measure, which is the thing we're interested in. We want to forecast tourism demand by region, state, and purpose for the next few quarters. And at the top, you see there's 24,000 rows, there's 5 columns, and it's quarterly data. So the time spacing is 1Q, 1 quarter. So the sort of data that I often see when I'm doing consulting projects or working with organisations is it's often sub-daily data. It's not often yearly or quarterly or monthly, although it sometimes is, as my second example was, but often it's daily or even hourly or half-hourly. There's often multiple keys, so there's more than one series that you're wanting to be forecasting. Because it's sub-daily data, there's often multiple seasonalities you have to think about. It's not just an annual seasonal pattern, but you will often have a time of day pattern, a time of week pattern, and a time of year pattern all working simultaneously. And you often have more than one measure. You have multiple measures for every combination of index and keys. So we devised a data structure called a tibble, which allows us to store and manipulate these types of time series in R. And it allows you to specify what variables are which variable is the index, what variables are keys, and what all the other variables are, which are measured variables. So that's what the tibble package does. The tibble package allows you to define these objects easily, to manipulate them easily, and it works with our other packages for graphing and summary statistics and decompositions and forecasting models and so on. So let me talk about the second package now, which is the FEASTS package. So the FEASTS package, FEASTS stands for Features and Statistics Using Time Series, FEASTS. And I'll just show you, many of you will have just heard Tianga's talk in which he talked quite a lot about different types of features. So I'll just, for those who didn't, tell you what a feature is of a time series and how we might use them. So this is a decomposition of a time series. So the time series itself is the quarterly number of people having holidays in the snowy mountains, which is a snowy region of Australia. You probably think of Australia as all deserts, but we do have some small mountains, not very big by European standards, but high enough to have snow and to have snow resorts, and people go skiing there. And so this is the number of people per quarter on holidays in the snowy mountains. And then that's split up into these 3 components: the trend, the seasonality, and the remainder. These 3 things add up to give you the trips. So it's a decomposition which gives you a smooth trend through the series, an almost periodic seasonal pattern. You'll see that it does change slowly through over time, but each year it's very, very similar to the previous year. So that's called the seasonal component. And then what's left over after removing the trend and seasonal component is the remainder series at the bottom. So that's an STL decomposition. And from that, we can compute various types of features. One of the features is the strength of the trend. So if you think about the trend here, if we remove the seasonality from the data, then all you're going to have left is the trend and the remainder. And so the ratio of the variances of the remainder to the variance of the remainder and the trend together will give you some idea of how strong the trend is. If the trend is strong, then the denominator is going to be large and the numerator will be small. If the trend is very weak, then this ratio will be close to 1. And so this measure of the trend strength will be close to 1. If you've got a strong trend, it'll be close to 0 if you've got a weak trend. You can do the same thing with seasonality, exactly the same thing, but using the seasonality plus the remainder on the denominator instead. And again, if that's close to 1, you've got a highly seasonal series. If it's close to 0, you've got a not very seasonal series. Okay, so these two things are called features. They're things you can compute from the time series, which tells you something about the data. So we can compute them in the feast package by using the features function. So we take the data set, which is stored as tourism, we pipe that into the features function. We say we want to do it on the trips variable, and we want to use the feat_STL function to whatever features it has. And it returns a whole pile of things: trend strength, seasonal strength, and a whole lot of other things. You can see there's 5 other variables that are not shown there. So these are all features computed from that data set. And then we can graph them, and we can look at graphs of seasonal strength versus trend strength. Tianga in her talk did that for about 5 or 6 series. So here we're doing it for all 304 series split up by state. And it's really just one line of code, the tourism piped into features, which gives you all of this information. And then the other 2 lines are the plotting lines. So it's very fast to compute lots of features on lots of series simultaneously. And you can see things like, just looking at these graphs, the blue points correspond to the holiday series. So holidays are more seasonal because they have higher seasonal strength than the other series. And you can see Western Australia has higher trended series than the other series. So you can start seeing information about individual series by studying the feature space. And we can do things like find the most seasonal time series. I'm not going to go through these I'm going to go through these quite quickly, but my slides are on my website if you want to grab the code and have a look yourselves. So finding the most seasonal time series, you find that the Snowy Mountains was actually the most seasonal series because people don't tend to go there other than during the ski season. The most trended series is one of the series from Western Australia. And then you can let's do a whole lot more features. So rather than just do those features, we can say, well, compute all the features you know about in the package. So it's the feature set is from the feast package. And then it gives us now a data frame with 51 columns. So there's 48 features and the 3 key variables. And we now have this high dimensional set of features with 1 row per time series, and each column represents a feature of the computed from those series. And then we can do a principal components decomposition, a little bit like Tianga was doing, and we can look for outliers and see what's going on. So let's plot the feature space. So here we are plotting 304 time series. Each dot is 1 series. It's a principal component decomposition. So it starts with the 48 features computed on that series, and then it does a projection onto 2D space so we can plot it easily. So each dot is one of those series, and you can see here's an outlier sitting out here. We get a whole lot of series on this arm, we get a whole lot of series on this arm, so you've got some interesting differences between these 2 things, and then you've got 1 series which doesn't really fit with the other ones. And so the next question is, well, what's going on there? What's causing these 2 arms, and what's causing this one to be different from the other series? So you can explore your space of time series using standard data analysis tools. So I could, for example, colour these plots by state and thinking that might tell me something. Well, all it tells me is that unusual series is from Western Australia, but that doesn't tell me anything about these two arms because there's no sort of obvious colour differentiation between them. If I colour the two groups by purpose, then I immediately see that these are the holiday ones on this arm and all of the other ones are down here. And this one out here was a holiday series. So we now know it's in Western Australia and it's a holiday series. And it's an unusual holiday series because it doesn't lie on the arm like most of the others do. And down here, there's another unusual holiday series, which sits at the end of the other arm. That's a bit unusual as well. So if you've got a lot of series and you can't look at each of them individually, this is a way of finding where the interesting things might be to focus your attention. And you can go and look for the unusual one. So let's look to see what's happening there. And that's holidays in southwest of Western Australia, which is a wine region on the far west of the country. And there's something unusual about that one, which we probably want to explore if we were wanting to take this further. Let me now switch to forecasting, which is the third of the three packages I mentioned. Sybil allows you to do the data structures. Feasts does these feature analyses, decompositions and computing features on the series and some graphical tools, which I haven't shown. And the forecasting is in the Fable package. So Tibble standard for time series Tibbles. Feast stands for features and statistics for time series. Fable stands for forecasting tables. And it's a play on the word fable because a fable is a story that's not true, but it tells you something that's useful about reality. There's something real about it that helps you understand reality better. And that's what a forecast is. It's not the truth, because you haven't seen that yet, but it tells you something important about the truth, about reality. Before I show you the Fable package, let me just briefly say what I mean by a forecast, because people mean different things when they say forecast. For our purposes, for the Fable package, a forecast is an estimate of the probability distribution of the variable to be observed in the future. Okay, let's just unpack that a little bit. So here's a time series. This is the total number of Australian domestic overnight trips per quarter over a couple of decades. And I fit a model to that series, to the black data. I fit an ETS model, an exponential smoothing model, and I can simulate future observations from that model to get a possible future. So this is what could happen. This is one possible future that could occur given this series using an ETS model. If I use the same model and I simulate again, I get a different possible future, the same parameter values, the same fitted model, but running forward with different stochastic inputs gives me a different future, a different possible way the future could unravel. And so I can keep doing that. I can just start computing lots of futures and I get an idea what the possible probability distribution of futures is. Each of these has equal probability. And when I put it all together, I have an idea of what the distribution of the future is at each future time period. And so I can then compute, for example, the average future, which is the blue line. So that's the average of all my possible simulated futures. The dark blue region is a 50% region, which contains 50% of all of the possible futures. And the light blue region is a 95% region. It contains 95% of all of the possible futures, which means that there's still a small chance that it's outside those. And you can see the futures that are outside my 95% region still showing through there. So that's what I mean by a forecast. I mean the probability distributions, not just one number, but the whole distribution. If we zoom in a little bit, you can see more clearly the seasonal pattern here, which has been modelled on the training data. And you can see the uncertainty as it grows over time, because the further ahead you go, the more uncertain you're going to be, the less you know about what's going to happen. And then we can look at what actually did happen, because this is forecasts using data up until the end of 2017. So I can look at what did happen in 2018, 2019, and so on. And you can see how good your forecast is by how close it is to the mean, and you can also see how good it is at estimating uncertainty by looking at how well your prediction intervals, how frequently they contain the truth. You would expect the true value to be inside the dark blue region 50% of the time. If it's inside the dark region more than 50% of the time, that's not a good forecast. And if it's outside the light blue region more than 5% of the time, that's not a good forecast. The forecast should capture the uncertainty in the forecast should capture the variation in the actual data accurately with the right probabilities. Okay, how did I do this? So let me show you what the code looks like in Fable. So I take my data set. Remember, that contains 304 series, so there's a lot of data in there. I'm going to only use the data up until 2015 for this exercise. So I filter out only data up till 2015. I'm going to fit two models, an exponential smoothing model and an ARIMA model, to every series independently. And it can be a different model for every series. It's not fitting one model, it's fitting 304 ETS models and 304 ARIMA models. And you can see from the output that it's fitted a different ETS model for each of the combinations of region, state, and purpose, and a different ARIMA model for each combination. So very quickly, you have a large lot of models. And then you might want to do a combination. You might want to say, well, I'm also interested in the average of the two. And so we can have an ensemble forecast, which is, and you can just simply say ETS plus ARIMA divided by 2, and it will compute a combination of the forecast distributions computed from these two models. So it's an ensemble. It takes a mixture distribution of the resulting forecast distributions, and that's just a single line to do that. So you see how powerful the syntax is in generating a lot of forecasts very quickly. And then you take that object, the fitted model, and you pipe it into the forecast function, and it will then produce forecasts on every model for every series. So there's 912 models and series here, because there's three models, the ETS model, the ARIMA model, and the combination, and there's 304 series, which gives us, and the 2 years means it's giving us 8 forecasts for each of those combinations. Notice that understands natural language. 2 years as a string, it's in quotes. You can use natural language there and it will understand what to do. Or you can put in a number in, you could put in 8 and it will do 8 quarters. When it comes back with the distribution, so see this column here, this is the forecast distribution. So you see it's a dist column, so it's a full distribution. It's not a number, it's a distribution. And it's a normal distribution with mean 136 and variance 902 for the first one, for example. And it also gives you the mean of it as a separate column, because that's often useful to work with the mean directly as your point forecast. But you do have all of the distributional information in there including for the ensemble model, which is a mixture. And then you can plot it, for example, and we can we can produce prediction intervals from the distribution, and we can have a look at how well our forecast did against the distribution, and so on. And then we can do evaluation. Haven't got a lot of time left, so I'm not going to go through how the evaluation works. I have some slides about how to do it, but I don't think I've got time to do that justice. So let me skip over some of that and talk about just showing you the syntax, and then we can answer some questions if you like. So you pipe the forecast into the accuracy function, and you say what the test data is. In fact, you can just give it the whole data set, because remember, we filtered out some of it and we said we're only going to take data up until 2015, but the tourism data contained more data than that. So when we pass the whole data set to the accuracy function, it will just find which time periods match the forecasts and use those in comparing them. And then you say what accuracy measures do you want to use? So we're going to use the mean squared error and continuous rank probability score. So the mean squared error is a good measure for the mean, and continuous rank probability score is a measure of the whole distribution. How accurate is your whole distribution? And smaller is better. And so we've now got a mean squared error for every series and every model, and CRPS for every series and every model. And then you might want to summarize those off. Before I summarize them, because these are all on different scales. Like a lot of people go to some states and not many people go to other states. It's hard to compare mean squared errors across series. So we compute skill scores instead. So that's comparing these values with what you'd get with a naive model. And then we can average them. So we just group by model and average them. And you can see which models do best. So overall, the ensemble model, the ARIMA model does best on point forecasts, and it does better on the CRPS as well. Sorry, I've got that the wrong way around. Skill scores as good as high as good, because it's telling you how skillful the model is, how much it improves over the naive model. So wrong way around. The ETS model is the best because it has a higher skill score, and the CRPS is about the same for ETS or the ensemble. Okay, let me just do a shout out to the two awesome developers that I've worked with, Eero Wang, who wrote the Tibble package, and Mitchell O'Hara Wild, who's done most of the work on the Fable and Feasts package. And there's quite a lot of papers that underpin this work, and my slides are available on my website. The packages are available on the Tidyverts website. And there's a textbook which uses these packages. So there's a full undergraduate textbook to explain the methods, to explain how to use the packages with lots and lots of examples. It's free, and it's at otex.com/FPP3. And we'll stop there. I've got a few minutes for questions. Thank you.
Rob, thank you very much. That was excellent, excellent presentation. But I personally admit that I feel a bit of the personal link to the forecast package, and it's very sad to see that it stopped being developed. But I understand that Tidyverts changed the paradigm of how we think about R, and also sometimes doing some things in forecast could be quite unwieldy, and new tools fix this, alleviate this issue. So
just to be clear, the forecast package is not going to go away. I'm going to continue bug fixing and keeping it maintained and working. I'm just not going to add any new features to it.
Thank you very much. And one question from the audience: how does Feast handle multiple seasonality within a univariate time series?
So when you do an STL decomposition using Feasts, it will automatically detect multiple seasonal patterns. So it will, if you give it daily data, for example, it will fit a weekly seasonality and a yearly seasonality. If you give it hourly data, it will fit a daily seasonality, weekly seasonality, and annual seasonality by default. You can override that and say you don't want them all, but that's the default. And so when it produces seasonal strength, it will produce one for each of the seasonalities. That's completely automated.
Okay, folks, we are out of time, unfortunately, but your questions can be asked again during the forecasting and prediction panel, which starts in a minute. So thank you very much for being with us. Thank you again for being with us, Rob, and see you on the panel.
Thank you.